Hi folks, welcome to lecture 1.2, part 1. We're looking at section 1.2, units and measurement. I wanted to start off with a couple of quotes, one from the previous edition of your textbook and one from the current edition of your textbook, just to look at why this is important and to motivate what we're doing. So the first one says, medical professionals make measurements every day, whether to obtain a patient's weight, take a patient's temperature or blood pressure, or administer a particular dose of medication. Is that right? Yes, that is absolutely right. That is true. The second quote is from your edition of the textbook, and it says, if you are working in the healthcare field, you will take measurements routinely, perform calculations that are critical to the health of your patients, such as dosage calculations. Developing the skills learned in this chapter is a basic part of your training and also central to understanding chemistry. So we're going to jump right in to talk about units and measurements. And a measurement consists of two parts, always, a number and a unit. Okay? We never have naked numbers here. They're always clothed with a unit. So in math class, you will encounter simply numbers. In science class, numbers almost always have a unit with them because they represent something physical and real. Here's an example from my child. This was when he was, I guess, 2 years old, maybe a year and a half. It looks like here. I kind of forget. So you can see, right, his weight. It's given passed through time. He's growing quite nicely. Um, his weight is given in pounds, right? Not just 26, but 26 pounds. Because if I didn't put pounds there, we wouldn't know what it meant. Height is given here in inches. Okay. If we look at some of the other units here, we have temperature, 100 degrees Fahrenheit. However, these two do not have a unit. What is up with that? It's breaking the rules. Pulse and respiration don't have a unit. But I think that's just because we all know what that is. That's breaths per minute and beats per minute. So since it's a given, they're not actually showing the units, but you know those numbers have to have units. Now, when the doctors gave this report to us, it was weight in pounds and height in inches. But I know for a fact, because I watched them, they measured his mass in kilograms and they measured his length in centimeters. But they gave it to me, the patient, in pounds and inches. So this is something that's going to be important for us to think about. Is what do your patients understand? Which units do they understand? Because there's different sets of units, right? So in science, we're going to use the metric system. And we're going to use SI units, which are standard international units. And these are going to be different than the units that your patients and maybe you understand best, right? So some of the fundamental physical quantities that we can measure, like mass, in science and in medicine, you're going to use a kilogram. But what we're used to is pounds. So if you want to be in science and health, but you also want to interact with patients and give them information that they understand, you need to know how to go back and forth between those. That's called converting, right? Length. In the metric, scientific, medicinal field, we use meters or variations of meter. But things like inches and feet is what makes more sense to your patients. Time is always the second, so that's kind of nice. In the metric system and the English system, we both use seconds. Temperature. In science, we use Kelvin, which is similar to Celsius, but slightly different, and we'll get to that later. But we definitely don't use Fahrenheit. But if you tell your patients they have a temperature of 100, that's what they're expecting. If you tell them they have a temperature of 37, they don't know what you're talking about. So we need to go back and forth between Celsius and Fahrenheit. And the last physical quantity is the amount of something. And here in science, we'll use the mole. And there's not really an equivalent to that in English. maybe like a dozen. That's the example I give a lot. Thinking of a mole, it's just a number. But um, yeah, so one day I was at the doctor's office and at the University of Iowa and saw this above the scale. And I pulled out my phone and took a picture. So it says that our scales report grams and kilograms only. Why is that? Why does medicine use kilograms? That's so confusing to the patient. Well, it's actually to help prevent errors. Dosage amounts for many medicines are based on kilograms. That's what it says right here, right? Using just one type of measurement helps us avoid conversion errors and improves the safety of the care you receive. So if you're standing on the scale, it would give you kilograms, and so they put this basically a quick and dirty conversion chart up. So if you're standing on the scale and it tells you that you weigh 80 kilograms, you know that you're 176 pounds because most Americans, if you say you're 80 kilograms, they have no idea what you're talking about. So these conversions are important. And we do these conversions like this says because we want to have a single type of measurement used in science. So the nice thing about the metric system are that one set of units is used for all types of measurements because they're scalable by prefixes. So grams and kilograms, meters, kilometers, things like that. Makes the conversion simple. If you're within the metric system, you're just moving the decimal point. Things like 12 inches per foot is not an easy conversion, but 100 centimeters per meters is a very easy conversion. And another thing about this, by the way, you all know the whole world uses it except us. The United States is the holdout. So as I said, one of the benefits is that the metric system is scalable by prefixes. And so here's what I mean by that. This is showing length or size in meters and showing some of the prefixes. So here at the right is an adult female, 1.65 meters. So what are the odds that a human female just happens to be on the scale of 1 meter? It's crazy. What are the odds? Well, they're actually pretty good, right? Because we just made this whole thing up, right? The length of 1 meter was determined and decided upon by us, by humans, right? So it makes sense that the things that are our scale, things that you can hold in your hand, things that are about the size of you, are often given a value close to 1, and then things that are smaller than take smaller numbers and bigger, much bigger numbers. So we're like the center point of all of these scales because we invented them, right? The concept of length is a real thing, but how you choose to measure it and what unit you have is completely arbitrary and made up. But once it was decided, now we have standard, and this is what we have. So you can see the numbers are in scientific notation, 10 raised to powers. So that's simply moving the decimal point to the left. So for the example I'm pointing to here is centimeters. 10 to the minus 2 is basically saying 1 over 10 squared, which is 1 over 100, 0.01. So 1 centimeter is 0.01 meters. We'll do a lot more practice with this. A drop of blood is about a millimeter, and that's 10 to the minus 3. Notice we keep going down 10 times smaller here. When you get down to 10 to the minus 6, it's micrometers. That's around the size of a blood cell. A few more orders of magnitude smaller. When you get to around nanometers, just 10 to the minus 9, we're on the size of molecules. And another 10 to the minus 10 is about the size of an atom. So 10 to the minus 12 would be about 100 picometers would be the size of an atom. So these numbers are really, really small when you look down here. And writing out 0.000000001 and trying to keep track of that is not easy. And so that's the benefit of scientific notation. Instead of all those zeros, we just write 10 to the minus 9. And that means you take 10, or you take 1 and move the decimal point 9 places over to make it smaller. So not only the scientific notation is really worth learning so you can avoid these big and small numbers, but also then we can use the metric prefixes to talk about numbers that are easier to understand and to say. Here's another example. So let's look at the appropriate metric units to avoid all these zeros. Big and small, right? The first is a diameter of a drop of blood on the head of a pin. If we're just in the base unit of meters, it's 0.001 meters. But to avoid all those zeros, it's 1 millimeter, right? So a millimeter is 1,000th of a meter. Going smaller, the diameter of a blood cell is 0.000001. And that's hard to keep track of. Notice sometimes you put a space every 3 decimals to help us see the spacing, but it's still hard. I would much rather say 1 micrometer. Now, this also works with big numbers, right? Like the memory of your hard drive is a trillion bytes. Well, trillion, or 10 to the 9, has a special name as well, which is a terabyte, right? So maybe you're familiar with that. A terabyte is equal to 1,000 gigabytes, by the way. And 1 gigabyte is 1,000 megabytes. All of these prefixes show up in tables like this one. Okay, now, like I've said this before, you do not have to memorize this. Something like this would always be given to you, but you have to know how to interpret it and use it. So I'm going to stop this here, and on part 2, we're going to start with this table and talk about it.